In this video, we are going to discuss the code for quicksort. So what I've done is I've translated the algorithm for the partition method that equates to this part of the code, which is our partition method. And the quicksort method is our main method, which will be actually called in our driver program that technically will call something like quicksort array, like let's call it a with 0 comma length minus 1, as we saw in the merge sort. So we check this condition whether our low is less than high. And why we are doing that is if we have a sub array that is of length 1 that's exactly sorted, as we explained to you in the merge sort videos. So what we first do is we find out the pivot by calling our partition method with the low and high. And then what we are going to do is we are going to recursively call the quick sort on the left half, which is from low to pivot minus 1, and the right half, which is from pivot plus 1 to high. The entire code along with the driver function is given right here. So in the partition method, what we are exactly doing is we are first defining our pivot as the first element. So this is our strategy, which is array of low. In case you want to choose some pivot, which is the median or the last, you just have to change the line of code right here. Other lines would typically remain the same. Next, what we are going to do is we are defining the up to low and down to high. So in this case, we'll have, like, let's say if you have an array that has these numbers, we are going to define up to the low and down to the end of the array. So you can define it to low, or you can define it to low plus 1, because low is the pivot element. It doesn't matter because there's one less, there's a less than symbol here, not the greater less than equal to. If it was less than equal to, you should define this to low plus 1. Now what we are going to do is we are going to move our up pointer till we find an element in our array that's greater than the pivot. Once we have found the element that's greater than the pivot, we break right there. Next, what we are going to do in our next iteration, which is we have a new for loop that moves the down pointer towards the left. So in this case, we are going to break when we have found an element that's lesser than the pivot. Next, we are going to check if our up is less than down. So if that's true, then we are going to make a swap of the two elements. So once we have made the swap, it will go back up because we have just broken down from the indices, but we haven't passed each other, which is we'll stop when up is greater than down or up is equal to down. At the end, we are going to swap the element at the low index and the element at the down index, which is the element at the low index is actually our pivot. So we are basically swapping the element which is the pivot with the down pointer, as we saw in our previous video's explanation. So the entire code with the driver program is again at this link. If anybody wants to check it out, do check it out. Uh, I'm not going to give you a walkthrough of this because it's pretty similar to the merge sort. Again, like once you have finished this code on a smaller array, you're going to stop right here, and then the recursive calls will call the left half and the right half, very similar to the merge sort. So it's going to work. The time complexity of quicksort is O n log n on average. And this algorithm is used much more in like almost all different libraries somehow implement quicksort for common sorting tasks. So it's an important algorithm. Now, if the pivot value is a random value selected from the current sub array, then statistically half of the elements will be less than the pivot and half will be greater. So, thus, what will happen is there will be log n levels of recursion in the average case. But in the best case, in the worst case, what will happen is If we pick the pivot, like let's say if we pick a pivot, and if no elements move towards the left or no elements move towards the right, which is like, let's say if you have a pivot like this, and after the end of the pivot, all the elements stay where they were in the end, that is a worst case of quicksort, and that will have like that will take O n square time to execute the entire algorithm. So the overall time complexity for this algorithm is O n square in the worst case, O n log n in the average case, and O n log n in the best case, similar to merge sort. But now we do not require new space allocation to perform this algorithm like in merge sort. We do require O log n space, and that space is the recursion stack, but it has nothing to do with additional memory that we are going to initialize. So in merge sort, our total space that we consumed was on to create new memory to sort to merge the list, plus we had this o log n, which was the number of recursion calls in our call stack. But now it will be just o log n in the worst case. So we do not require new space initialization. The only initial the space we require is in the recursion stack. So that's pretty much it for quicksort. We have a few other types of sort, which is sleep sort, counting, Tim, radix, and bucket. We won't be covering them in the course, but if you are interested, try to like search these on the web. They are pretty straightforward. Some of them are linear in nature, which is we have seen most of the sorts that are o log n, o n log n, or o n square, which is quadratic ones. O n log n is kind of the minimum. Like if we see, there's a theoretical proof that sorting cannot be done in less than n log n, which is we have this omega constraint that the worst case, like in the best case, it could be like n log n. But these sorts actually can be performed in on, and the reason why they can be performed in on is because they are peculiar to the type of the input, which is they are dependent on somehow on the type of input. Like in the case of sleep sort, what we do is, like let's say if you have some numbers like 5, 8, 4, and 15, like let's say if it is this, if I were to sort this, I would just put like a timer on this, which is sleep 5 and then sleep 8. So in this case, what the computer is going to do is it's going to print the number 5 after 5 seconds, 8 after 8 seconds. So it's sorted, but it's kind of like simulating it, and it's not practically used. Counting sort is again like it can be done in on. How it works is you have these numbers. Like let's say if we know the range of the numbers before we start the algorithm, like we have numbers from 0 to 10,000. What we can do is we can create an array with values 0 through 10,000. And if our array looks something like this, which is 9, 8, 1, and let's say 10,000, so in that case, at the place in the array, we are going to increment the count of that number by 1, which is in this case 1 would be 1, 9 and 8 would also be 1, and then 10,000 would be 1 as well. Now, the issue here is we are wasting a lot of space. Like if we do not see numbers, those numbers would look something like zeros, and we are wasting a lot of space. So again, that's not commonly used, but if something is more dense, it can be used, and we can do this in O of n, time complexity. For radix sort is again a version of counting sort with the radices, and bucket sort is also similar to them. Tim sort is a new algorithm that is widely used nowadays. I think Java implements Tim sort behind the scenes for sorting. So just check these out. If you have any questions, uh, feel free to ask me. These algorithms won't be a part of the exam, they are just out of interest. So these are some of the resources to help you visualize the algorithm. Check them out, they are pretty great. And if you have any questions, feel free to contact me in the office hours. Thank you.